Welcome to the GaN Talk podcast, brought to you by EPC and hosted by Maurizio Di Paolo Emilio, Marcom Director at EPC. This show brings to life the stories behind GaN technologies and products. In each episode, you'll hear engineers, executives, and academics share insights on the challenges and opportunities shaping the GaN market. Here is your host, Maurizio Di Paolo Emilio.
Hello everyone and welcome to this new episode of GaN Talk podcast. Today we explore how adaptive computing is transforming onboard satellite intelligence, signal processing and AI in orbit. With space VPX platforms like ADM BB630 and ADM BA601, Alpha Data is enabling scalable radiation-hardened compute architectures built around AMD Versal Adaptive System on Chips. A particularly important element of these platforms is their radiation-hardened power architecture, developed using GaN-based solutions from EPC space, which help deliver higher efficiency, improved power density, and robustness in harsh orbital environments, key enablers for next-generation spacecraft compute infrastructure. Together, adaptive processing and advanced GaN power technologies are reshaping how satellites process data directly in space. It's a pleasure today to have a special guest, Colin Shire, electronics engineer at Alpha Data. Hi, Colin. Welcome aboard.
Hi, Maurizio. Happy to be here. So I'm an electronics engineer here at Alpha Data. Alpha Data we are specialized in FPGA hardware. We've been around since the 90s, and we're headquartered in Edinburgh, Scotland, but we have an office here in Littleton, Colorado as well, primarily to service the American aerospace and defense market. Mm-hmm. We're a long time partner with AMD, formerly Xilinx, for FPGA hardware. So we get special access to some of the devices a little bit ahead of market, and we're a strategic partner with AMD to deliver deployable solutions with some of their most cutting edge devices. We don't just do aerospace and defense. We have a near even split between A&D as well as data center type products. Though rugged VPX and XMC form factor cards have been a major pillar of the business for years now.
Thank you. So I have prepared a couple of questions to share with you. So let's start with the first one. So as you know, spacecraft architectures are evolving from fixed function electronics toward flexible onboard processing, capable of supporting AI inference, sensor fusion, dynamic communications workloads. So what are the main mission level drivers pushing spacecraft designers towards adaptive compute platform like your solution that I mentioned at the start, ADM BB630 and ADM BA601, so instead of traditional space-qualified processing architectures?
Yeah, like you said, it's really about flexibility. FPGAs have been popular in space for a long time because they are so flexible. You can qualify one device and then have it do multiple things across multiple missions. One of the interesting things about the new Versal devices is just how fast they are. They're orders of magnitude more capable and faster than previous devices like the Rad 750 or more legacy FPGAs. So you can process and move much more data. The other thing is being an adaptable device, you can now explore this idea of a software-defined satellite, which we're starting to see enter the market. You can have a common spacecraft with common avionics doing different things across different missions, where you only have to develop the bus or the box once. And then being software-defined, you can redefine what the satellite does after launch, which is a really powerful capability.
Thank you, Colin. So as compute density increases, traditional silicon power stages can become a bottleneck in terms of efficiency and thermal constraints. So my question is, what makes GaN particularly well suited for powering adaptive compute platforms in radiation-hardened space VPX environments compared with the conventional silicon-based solutions?
Yeah, so as the transistor feature size decreases on the main SoC, your core voltage goes down to power all those gates, but your power stays roughly the same, if not increases, which means that your current also increases. Sorry. This means that your power supply needs to be able to handle more and more currents as your SoC gets more capable. So it boils down to current density and losses in the power supply, where GaN particularly excels. The low RDS on and gate charge of a gallium nitride transistor is just fantastic for this kind of thing.
Can you tell us more about the collaboration with EPC Space and how their radiation-hardened GaN solutions contributed to the power architectures of your solutions that we have already mentioned?
So it was actually a three-way partnership between Alpha Data, EPC Space, and TI. EPC provided the 7019G power transistors for both platforms, the 630 and 601. And they've been fantastic devices, offering, like I said earlier, the low RDS on and gate charge. So we've seen very high efficiencies on this core power supply design that we've implemented on our boards. With a modern SoC and thus modern SBC, your density is very critical. We have to use very small passives to fit everything onto the board. And EPC Space has offered us the current density needed to pack everything into these small boards. For a sense of scale, the VA601 card can consume upwards of 200 amps from its core supply. So we do need to move a lot of charge around to feed these versatile devices. And of course, this is all before you look at radiation, where, as you know, the EPC GaN devices perform quite well in both TID and single event effects.
So, power and the power architecture choices influence not only efficiency, but also integration flexibility across payload and platform subsystems. So, from a spacecraft integrator's perspective, what system level advantages in terms of EPC space GaN technology would bring? Talking about switching frequency capability, thermal performance, swap optimization.
Yeah, so I'm hammering the point home here. The power and current density that's enabled by GaN is just crazy. With a low RDS on, you can have smaller packages because you have less heat to dissipate from the transistor itself. Low gate charge reduces your switching losses, and both of these together allow the packages to be very dense. I've poked around the rad hard power MOSFET segment, and a similarly rated silicon MOSFET tends to come in a much larger package with many times the on resistance, which would dramatically increase the losses in the supply. This doesn't just affect a core power supply for an SoC. If any kind of power switching for a motor driver to drive like a solar array pointing system, or just discrete power switches within another spacecraft box, you have to consider the losses in all of these systems. In spacecraft design, I like to think that weight and power are very tightly coupled. The more power you have to get rid of, the more weight you need for an infrastructure for cooling. Every watt counts to the integrator because it means more mass, which it's all a very dynamic and interconnected system.
So, thank you, Colin. In conclusion, looking forward, adaptive computing and advanced power architectures are converging to support more autonomous spacecraft. How do you see the combination of adaptive versatile-based compute and radiation-hardened GaN power solutions evolving over the next generation of satellite platforms?
So we've been doing inference computing on FPGAs for a little while now, but with the SoCs that AMD has been producing recently, and the addition of the AI engines, the vector processors, you can do very efficient inference compute on orbit. We actually produced a white paper demonstrating anomaly detection in spacecraft telemetry data using the AI engines on VA601 or VP630. I can't remember which one offhand. They're functionally the processors are functionally the same. The AI engines, that is. You just have more of them on the Versal core on VA601. And the Versal is just so capable. With the larger Versal core, able to crunch through terabits of data per second. I think the overall space industry is going to use more and more communications, especially optical communications. Most notably, I think, is the Starlink constellation and the recent Artemis 2 flight use optical interconnects both between spacecraft and also down to the ground to move vastly more data over longer distances than traditional RF. Versal it has the data rate, right? The gigabit transceivers can do like 25 gig per pair. You can move just gobs of data into and out of an optical interconnect. So I think we're going to see more communication between spacecraft to enable more orbital processing between spacecraft, as well as offloading compute resources to the spacecraft instead of having to fight for bandwidth to get it back down to the ground for processing. We see inference compute is wildly popular across the entire tech industry right now, and it is making its way into spacecraft. Like I said, we've demonstrated this on our hardware. And I expect Versal to be uniquely positioned to serve this demand. And again, of course, we'll make the processors work.
Yeah, and just let's conclude with a few key takeaways in terms of GaN for space. So we will say even more GaN for space in terms of power management systems.
Oh, absolutely. Density is always increasing. So, like I said earlier, every watt counts. You need every system to be as efficient as possible. And if you can reduce the losses in your supply, then that's more power you have for your compute or other actuation.
Thank you, Colin. Thanks a lot for joining us at GaN Talk podcast. Has been great talking with you, and I wish you a good day. See you next.
Yeah,
Thank you.
Thank you, Maurizio. Have a good day.